So, can you give us a little bit of an introduction of who you are, your background?
Sure. So I think you can place me at the intersection between technology and math. So my background is in telecom engineering, but then I also have a PhD in maths. And I started working at Siemens in Germany, kind of at a unit that was solving or tackling problems that had some advanced or required some advanced maths. And coming in from every business unit. So it could be, dimensioning networks, like fiber optic networks, mobile networks, or it could be even about dimensioning or planning electric grids or traffic in a city. So I took a lot of pleasure in solving those things, and so that's why I decided to go deeper into the maths and do the PhD. I also, during the PhD, it was a very intensive time. I think in 3 years, I did like 27 patents. And it was about modeling the backend of the internet, which is very exciting because it's actually, you use the same maths that you use to describe nature. So it's a special type of geometry that you use to, which is fractal geometry, that you use to describe complex stuff in nature, like leaves or branches of a tree. And the internet happens to be that one thing made by humans that is so complex that you require that special type of maths. I also did moved on to then working on compilers and design of domain specific languages for the banking sector, which then took me to artificial intelligence, machine learning. And then in 2013, I started working with cryptography from the industry perspective. So I started with zero knowledge proofs, and that ultimately took me to FHE and multi-party computation. And yeah, the last years I've been focusing on multi-party computation.
Oh wow, that's a lot of interesting things going on
Yeah,
over
yeah.
there. I guess the math itself is probably what drove you to crypto, and now you are a founder of Nillion. So, what happened in the meantime from getting really interested into crypto to starting your own project in the space?
Yeah. So I think it can be, if I had to summarize it in one word, it would be Andrew Masanto. That's what happened. So I met him back in 2017, I think, through a VC. And back then we started exploring the idea of applying different types of cryptography to different problems in the Web3 space. So he's very well known for founding Hedera, Hashgraph, Reserve, and other multi-billion-dollar businesses in the space. So he really has this special talent of spotting the right opportunity. Back then, we were thinking about designing a privacy coin along the lines of Zcash and Monero, but he kind of said it's not really the time. And actually, it turned out to be correct because it was the end of the crypto summer. Crypto winter came in right afterward. But we kept in touch very frequently. And then in 2021, we started talking about MPC, like using MPC and applying it to Web3. And we got really excited about some mathematical ideas I had been working on. And he brought in Alex Page, the CEO of Nillion, and Andrew Yo, the chief marketing officer. And we did some brainstorming as to how that piece of math, which is really abstract, could actually turn into a technology, into some platform or infrastructure for Web3 applications. And that was the beginning of Nillion. And I guess the vision that we were contemplating back then was kind of to tackle an unwritten rule of the internet, which is that every time you have to interact with a service provider in the internet, you have to give them a piece of yourself. You have to, some details about yourself, your data, your personal identity will get transferred over to that company running that service. And it's a moment in time that cannot be taken back. It's irreversible. So you've lost control of that information. They can do with it whatever they want. And this kind of permeates through the whole chain of actors. It doesn't only affect users, it also affects companies and governments. And because of that, also, many companies are, for example, not collaborating because it means that they have to share information. And there's, reasons not to do that because you don't want to censor or share your sensitive data, or maybe there's regulations that prevent you from doing that. So, because of that, we live in an internet that is made of siloed data, siloed information, and that is kind of stressing out the competitive side of businesses and people, but not the collaborative side of businesses and people. And that's what we like about decentralization, which it is community oriented, and that's where we thought, well, this could be the perfect match to get this technology, which is removing trust and adding this security, so that you can collaborate without sharing, and now combine it with Web3, which is all about community and collaboration and also trust minimization. This could be a perfect match, and we kind of then set ourselves to create this public decentralized platform for secure storage and compute of sensitive information, whatever that may be. It can be from people, it can be from companies, from government. So that was a little bit kind of the thought process that took us to, or me in particular, to embark on this adventure.
Yeah, there's a lot to unpack in there.
Yes.
Um, so I think we can start by kind of giving a preface of what is NPC, and maybe from here onwards, every time you mention an acronym, we can kind of highlight what it means as well. Because I think a lot of people are not really familiar with a lot of the technologies that underpin what you guys are developing. So I think that's going to be really helpful.
Yeah.
Um,
That's a very good idea, and actually it's a bit confusing, in Web3, because to begin with, we talk about cryptography with two different meanings. One is the mathematical cryptography, the other one is the crypto space. So to begin with, there's a little bit of confusion there. Then people tend to think that cryptography, the math one, is just zero knowledge proofs, which is it's the most prevalent privacy enhancing technology used nowadays in the Web3 space, and that's the reason why. But there's others. There's other PETs or PETs, privacy enhancing technologies, that are very interesting indeed. You have fully homomorphic encryption, you have differential privacy, you have multi-party computation. So that takes us to this MPC acronym. What it means is any type of computation where there is many parties, so there's many nodes, each one controlled usually by a different company or entity, and they collaborate to compute jointly some sort of function, or run together some sort of program, but with the caveat that they are not actually sharing the inputs that they contribute to for the execution of this program. So they're able to maintain the privacy or confidentiality of their inputs, and come up with the result from that computation, but without really running it on a single computer. That's one difference compared to other privacy enhancing technologies like FHE. FHE, the typical setup, you have a client on a server. The server runs a computation. The server cannot see the data it's computing on. But here we're talking about a network. So that's why it is kind of closer to the decentralized notion that we already see in Web3, where we typically have many nodes collaborating, running a blockchain, or some other sort of construct.
yeah, awesome. I think before we get more into the weeds of those differences, can we get a brief overview or a high level review of what it is, what Nillion is, and what it can do from like a practical standpoint?
Yeah, so essentially it's a Web3 infrastructure. So meaning that there is not a single node that runs the whole thing. There's a network. And the network is not controlled by us. It's comprised of different nodes run by different entities. There's a process for nodes to and kind of enroll into the network, that we can discuss if you want. But the idea is that we are not in control of the network, nor do we want to be in control of the project. So this project will be handed over to a Swiss association, and that's where governance will take place. That's where the important decisions going forward will be taken, and token holders will have a say in that. So it is a decentralized infrastructure. Now, the difference compared to something like a blockchain is that we are here talking about general compute and storage. So we are tackling the problem of computing things on this infrastructure without sharing or revealing the information. Because the one thing that is typically missing from existing Web3 applications is that confidentiality. So many of them are public. What you put on a blockchain, everyone can see, and that has very good advantages because you can have traceability and auditability and things like that. So it is good for certain applications. But if you think about the typical application in Web2, without confidentiality, it wouldn't be possible, because if every user saw the information from other users, you could you yeah, I mean you couldn't build half of the businesses that you've built on Web2. So what we're trying to do is to bring in that important ingredient into the Web3 mix, so that now people can build that type of business that you would see on Web2, with that essential ingredient, which is confidentiality, but on a decentralized infrastructure, if that makes sense.
Yeah, yeah, I think that made a lot of sense, and it's awesome. So, what can emerge from that sort of from what kind of possibilities can emerge from that? What are the practical things that can happen having that kind of capabilities on a technological level?
So you can think of it from different angles. Like from the Web3 angle, it's essentially about adding this confidentiality to it. So you can be thinking about private smart contract execution. You can be thinking about adding privacy to NFTs. You can be thinking about things like signatures or threshold signatures. You can think about private voting, like DAO management, but without really showing the information of who's voting for what. So there's a number of applications you can find in the space. If you think beyond the current scope of Web3, then you would be essentially thinking about adding the decentralization element to existing type of business applications or business problems. So there you're thinking about the problem of storing information, but without really wanting it to give it to the company. So what all the sensitive stuff, can I store it somewhere that doesn't reveal it to a single entity, but is kind of maintained by a group of nodes with enough guarantees as to the reliability and of the data and so on. But you can also go beyond that and say, well, actually, I not only want to store information, I also want to compute on it. So I want to have my, I don't know, medical records, and I want to run computations or let companies run computations on my medical records. So there's a lot of examples on that front as well. And we're kind of tackling both, probably giving more importance to the Web3 use cases first, because of the community. They're really open to new technology, and they're already used to the concept of decentralization, but we're not closing the door to the other type of use case as well.
Yeah, I think that's really amazing. It's kind of the best of the both worlds. You can have the decentralization aspect, but also have it privately done, which is
Yes.
kind of like one of the main things that is missing, and that zero knowledge proofs are trying to address at the moment and cover this gap. But the Nillion approach is a sort of alternative to that that presents a perhaps more efficient way to compute it at a better speed.
Yeah, I would say it's complementary to zero knowledge proof, in the sense that zero knowledge proofs are really efficient and powerful. But you need the prover. So you have a prover and a verifier. The prover has access to the information and proves some statement on that information that the verifier can then check. For example, I can prove that, I don't know, my database has, or, the typical use case is that I prove that I'm older than 18 on a database of my personal information. But and this is great, but if you think about it in terms of computation, this is you're outputting one bit. It's either true or false. So that kind of limits the type of computation you can tackle with zero knowledge proof. Um, if you want to really have a primitive that allows you to store information and then do general compute on that information, and that no one, there's not a single figure or role of a prover that has access to that information in plain text, then you can go and actually go for multi-party computation solutions, because that's what they add to the mixed, and actually they can be combined. So if you can generate zero knowledge proofs in such a way that there is no prover, so you decentralize the prover by applying MPC to it, and now there's no one really having access to the plain text information to generate the zero knowledge proof. It's actually the MPC network generating that zero knowledge proof, or playing the role of a prover. So in essence, they're different. They're complementary. Each one is good at a different thing. Zero knowledge proofs can prove stuff, but MPC is closer to what we are used to think in terms of a place where I can store information and compute on it without revealing it to anyone.
Yeah, that's awesome. And obviously, this ability to do those type of calculations is something that we haven't had before. So, what's underpinning this breakthrough? What and how long have you been working on this?
For a while, for a big while. So we are. I mean, MPC is a thriving, I would say, field. There's a lot of innovation, lots of interesting projects. One of the important challenges is around the solving multiplications, because every computation that you can think of can be broken down into additions and multiplications. And existing protocols are really good at tackling additions, so linear operations that involve additions with of secret elements, or multiplications but with public elements. But the multiplication of private elements is the problem. So we focused on this problem and came up with a way of solving nonlinear parts, or circuits, or computations, meaning ones that have a lot of multiplications. And so what we see this innovation, or where we see it play out, is as a way of combining it with existing MPC technology, so that now all those parts of the computation that are mostly linear can be tackled with the very efficient existing protocols. But those parts which are really hard to solve because they involve a lot of multiplications, you can have this new cryptographic primitive that we are using to do that. So it's like a way of um, so kind of addressing one of the problems that MPC has, and providing a new means to tackle that, but also in a way that we are combining it with existing MPC as well.
Yeah, and what have been the biggest challenges on bringing this merge to life?
So yeah, that's it is. One of the things is that this is very complex stuff. So you require experts on a different number of topics. So one is the academic kind of cryptographers. Those are the ones who come up with new protocols and new mathematical ideas, and they write the proofs for the protocols, and they're actually aiming to advance the field theoretical foundations. They are required because they are the initial spark that create end up in the creation of a technology. But then you need a number of people in between. So you need also to have applied cryptographers who are more kind of hands-on interested in specific solutions and with very practical knowledge, and who understand nevertheless the output of the academic cryptographers, but are able to now frame that in terms of a more engineering solution. And then you need engineers. So there's a whole roadmap of things that need to happen from the idea to actually that thing becoming a technology. And in that roadmap, there's a lot of challenges. So it's not only the mathematical challenges that you need to address, it's also the engineering challenges. Like, for example, how this mathematical theory is able to address computations in terms of addition and multiplications, as I said before, or alternatively as Boolean circuits with AND gates and OR gates and so on. So this is a very low level type of computational solution. You need to raise the level in order for it to be useful. And that's the role of these applied cryptographers and engineers. And one of the things they have to come up with is to write a compiler, something that ingests kind of high level descriptions of the problems that you want to compute on, and then is able or are able to compile that down to that low level representation. And that in and of itself is a huge challenge, the writing of efficient compilers that are able to bridge that abstraction gap. And that's just one thing, which is not even touching the network side of things. So now you want to deploy that on a network with many parties, and that of course adds another level of complexity, because you need to handle communication between those parties. You need to handle the cases where parties are joining in or leaving the network. You need to handle cases where some of those parties are bad actors. They want to on purpose hijack your network. They want to either find secrets in your network or actually just mess up with your computations, and they just want to change the result from computations. So there's a lot of aspects and angles that need to be addressed in order for something abstract and initial to become actual technology that can be used by people. And those are those are the challenges that you find in that path.
It's almost like you have to find people that work on the intersection of different fields that are highly complex.
Yes.
So it's almost as if like you're creating a new sort of a specialty in a way.
Yeah.
Like
It's
you're operating the middle zone almost.
Yeah, that's very very accurate. Because it's like different languages, right? So the mathematicians speak one language, the engineers another one, and the typical thing you would do to solve that situation is to put an interpreter in the middle. But I don't think there's such a person who is really able to bridge that gap just with one person. So what you find instead is a number of people with varying degrees of expertise, or mix of knowledge between practical things and theoretical things. And then you need to move ideas from one end of the spectrum to the other end. And as they move, they start materializing themselves, initially into prototypes, then into test nets, and then ultimately into production networks. And this reminds me of this problem of the this is like the telephone problem, where you say a secret to one person, that person says it to another person, the other person to another person, and then the last person says the secret, and it's completely changed. It's completely different. So that's the risk of this approach, and that's why you need to tackle it with a very structured process in place, where you actually have formal documentation at all stages, and you have very well defined abstractions or artifacts that you're generating on each one of the stages. And ideally, when you see the end product, you're able to trace it back to the mathematical protocol and say, okay, this part here of the code is actually this part here on the math paper, so that you have the assurance or the guarantees that you haven't introduced vulnerabilities along the way. But it's a very interesting problem indeed. It has to do.
Yeah, I imagine your academic background came in really handy when you're trying to map out how to build this thing from the ground.
Yes, as well as of the engineering background that I also have from working in real companies, because you really need also that side of things. So you need to understand how a real engineering team works and what type of inputs do they require. So yeah, I was previously CTO of a tech company, and that has helped a lot for sure.
Yeah, I imagine. Um, I'd like to dive in a little bit on the main differences between Nillion and a traditional blockchain because it's such a foreign concept for what the industry has now that I think is a good way to kind of conceptualize it is to compare it to something that people know really well. So if we can dive in a little more on the differences and similarities there.
Yeah. So essentially, a blockchain is about getting consensus on a state. So there is this notion of a shared state of a ledger. A ledger is just database. You can think of it in terms of a database that contains transactions. And what nodes desire and wish for in this network is to agree on the state of that ledger. And to do that, they run a consensus mechanism or algorithm that involves some sort of communication. So they kind of there's different ways of doing that, but essentially at the end of that, what they get is an agreement on the state of that ledger. Now, this MPC based decentralized network is different to begin with because there is no single state, there's no global state that nodes need to agree on. Rather, there's groups of nodes that form clusters, and each one of them is operating in parallel. And what they're doing is taking data in protected mode, so it's kind of in confidential mode. They're not leaking information, and outputting data out. So doing stuff with that data and outputting it. So you can think of it in terms of a real computer that has different threads or CPUs, and they're actually like performing computations all the time in parallel. There is no need to reach this global consensus. There's no need for this global agreement, which makes this network behave very differently because it can grow more organically. Like you can set up new clusters without bothering the functioning of existing clusters because they're pretty independent. This is what Vitalik called logical decentralization. Is three axes. So there is the architectural decentralization, the political decentralization, and this is the logical decentralization. So it's the ability to break down the network in pieces and still get the behavior you want out of it. If you break a blockchain in two, you have by definition a forking of the blockchain, and it's not properly functioning as one; it's functioning as two. But if you but these units that I'm talking about in MPC are really independent, are pretty independent. So these clusters are able to perform their tasks in a pretty independent way. So that's a major difference. The other one is the purpose. So the purpose of the blockchain, as I said before, is consensus on the state of a ledger. The purpose of MPC network, decentralized one, is to compute. That's it, to store data and compute on it without revealing information, and both can be combined, and both I think need each other. So MPC requires blockchain because it will have some or the need for some coordination between the clusters, and the best way to do that coordination is by using a blockchain so that there is certain consensus coming out of that blockchain that establishes, kind of organizes the clusters. But also, MPC can help blockchain in a number of ways. Like it can add privacy or confidentiality to things that happen in a blockchain, starting from smart contracts, or maybe the way you want to interoperate or connect different blockchains. You can add some privacy into that as well. So both are complementary again, complementary concepts.
So it could act as even some sort of bridge between different blockchains, if I'm correct.
Yes. See, if you set up a bridge that makes use of smart contract that burns kind of tokens on the one hand and mints them on the other side because you want to move tokens from one to the other one, you could add privacy to that smart contract. Or if you want to move information, not just tokens from or events from one blockchain to the other one, you could also add some confidentiality by doing that on MPC technology. So that's one example.
And because it's centered around computation, that's the main use case, you could also theoretically deploy private smart contracts on Nillion as well.
Yes. So Nillion is not the platform to deploy smart contracts, but you can think of it as a layer you can place um, on existing smart contract platforms that can add privacy to them. So the computations taking place inside of a smart contract, you could outsource them to a Nillion network or to an MPC network, do them in that domain, and then bring back the result to the blockchain. So pretty much like a ZK rollup could work, or you could think of that in terms of also kind of MPC rollup. Although I would say that this use case is maybe um, not that interesting because ZK rollups are already very efficient, and ZK technology can do all this stuff in a very efficient way. But yeah, kind of ZK rollups are missing the confidentiality element. Although they're using zero knowledge proofs, they're not using it for privacy. And if you did need or require that privacy, then this kind of MPC based solution would be an answer. Would be definitely, I think, the best technology to tackle it.
Yeah, yeah, I think the privacy aspect is definitely a very important piece that is missing at the moment in the whole ecosystem.
Yes.
Um, is there one particular use case that you are really excited about that you guys can bring to life or facilitate?
So there's a difference between things we're doing and the thing I'm really excited about, which is kind of longer vision or longer term. So we're working with a number of FEs. We call them FEs. It means founder entrepreneurs. Those are people who want to start companies on a decentralized infrastructure, and they want to do some sort of compute on it. And we are really excited with them. I'm not really allowed to talk about them too much in detail, but they're really tackling interesting problems on different verticals, ranging from identity to communication to healthcare, and they need specific parts of that solution to have this trustless or trust minimized confidential infrastructure underpinning it. And so for that end, to that end, they're running things, or they're going to be running things such as biometric authentication. So you're not giving your biometric information to a central server. Once you do that, I mean, that you cannot take it back, and you cannot change your face or you cannot change your fingerprint, but rather you're storing that information in the decentralized network and are able to kind of work with the nodes together to perform computations on your biometric information. Or you have things like you know analysis on existing databases, like running cross correlation averages and things like that on data that you have. Or you have things like threshold signatures. So those are things that are coming in that we see in our pipeline of existing FEs. But the thing in more abstract terms that I'm excited about is providing technology that enables people to explore the collaboration aspect of businesses and individuals, because I think we're made of a mix of compete versus collaborate, and I feel that the existing infrastructure is emphasizing the compete aspect of it, because there's no technology that allows you to collaborate in a safe way. And I think this type of technology could be that, could offer that. And I hope to see in the future, new use cases coming in from individuals and companies and governments collaborating in ways that they haven't done before, because now they don't have to share information, but and yet they're able to kind of work together, not always compete, but also kind of also collaborate, to provide a better user experience, or for the better of the service.
Yeah, I think the possibilities for the sharing of data and research it's endless and can yield fruits in any sort of industry, any sort of research field. If there's a way to share information in that trustless manner, so many fields would be able to explode. Pretty much all the fields with the
Yes.
amount of data. Yeah, I think it'll be amazing. And one of the features that I think is really cool about this new primitive is the fact that it doesn't really, I mean, it does to some extent, but primarily it's not underpinned by encryption, but it's ITS. And if you can dive into that a little bit, I think that would be super interesting to hear about.
Yeah, so there's different degrees of security, in cryptography. Um, you know, Obfuscation would be like a lower type of security where you're hiding some information, but not really with any guarantees. For example, yeah, that's what you do when you obfuscate a JavaScript code in the browser. You can kind of compile it to make it really hard to read or understand, but you're not really preventing from its reconstruction. You're just making it very hard to do. Then you have a lot of cryptography based on what's called computational assumptions, and they're using some mathematical problem that people know it's hard to solve as the basis to construct or build the security of some protocol, so that now you need to break or solve that problem if you want to attack the protocol. And that would be the case of traditional encryption, the problem being in this case the factorization of the product of two large prime numbers. So if you were able to, given a huge number that turns out to be the product of two primes, to find out those two primes, then you would be able to break some of that encryption. That type of encryption is not quantum safe, so that computational problem in particular and some others are known to be solvable in an efficient way by future quantum computers. Then you still have computational security, but which is quantum safe. So this time it's still based on solving the difficulty of solving a hard problem, but this time there's no known quantum protocol or algorithm that can crack it, and so it's like a higher degree of security. And finally, you get another degree of security, which is called ITS, Information Theoretic Security, which means that there is no problem to solve. Really, there's nothing to tackle, to break. It's not based on the hardness of a problem, but rather is based on the ability to eliminate completely information from certain parts of the protocol. And one simple exponent of this, or example of this, is Shamir secret sharing, which is a way to break a secret down into different pieces. And it can be proven that if I'm given one of those pieces, actually, even if I'm given a few of them, there's nothing I can do with those to be able to learn anything about the secret that is hidden, through that partitioning of it into pieces. So, and this statement that there's nothing I can do, really applies to the cases where I'm equipped with infinite computational resources and power. So it's a very powerful security argument, and is kind of the golden standard in security. And there is some part of the technology of Nillion. So in this case, this protocol that we're talking about, that does offer this level of security, which makes it really interesting. In other, among other things, for the application to personal information that you really by no means want it to be, you know, broken into or hacked, even if people have enough economical resources to do that. And it's also helpful for compliance purposes because sometimes regulations forbid the use of things or encryption mechanisms that are reversible, that you can actually break in some way or form, like regular encryption.
Yeah, yeah, that makes sense. And you gave this example of Shamir, and I think you'll be interested to make a comparison with secure multi-party computation, because you know they're kind of like the two parts, if I understand it correctly, that you kind of use to come up with the Nillion breakthrough.
Yeah, yeah. So there's essentially three ways of building an MPC protocol. One is with Shamir type of technology, so it's called linear secret sharing. So you use it as the baseline, and then you build a MPC protocol. The other one is FHE, fully homomorphic encryption. Again, you use it as the baseline, and then you build the MPC protocol. And the other one is garbled circuits, which is another type of solution. So the linear secret sharing based solution is using typically Shamir. And what we did is to combine Shamir, or a linear secret sharing scheme, with another one that comes more from the FHE part. It's not fully homomorphic, but it has multiplicatively homomorphic properties. That's what we call a particle. And it's a cryptographic primitive that you can think of in terms of as encryption, but with ITS properties that hides information, turns it into ciphertexts, and then you're able to multiply those ciphertexts. And what you're doing under the hood is multiplying the plain texts that they're hiding. So you don't need to see the plain text messages to be able to multiply them. So that's what's called multiplicative homomorphic properties. So this technology that we're talking about actually combines those two primitives. Usually, Shamir was used on the secrets directly, but we're using instead particles on the secrets, and then the decryption key, which is what we call the blinding exponent. That's the thing that goes into Shamir. So we are actually combining those two primitives, and in doing so, we're able to tackle the problem of, you know, addressing multiplications, because this particle encryption scheme has these multiplicative homomorphic properties. It's very good at multiplications, and because we use the Shamir on operations that are only linear, that are never requiring multiplications, only additions, we are using it on the efficient side of the spectrum. So we're able to come up with a combination that is efficient in terms of what each primitive is able to do. And you can think of it in terms of somewhere in between linear secret sharing type of MPC protocols and maybe a little bit of homomorphic encryption based type of protocols.
Yeah, that sounds like you need so much context to kind of merge those things together.
Yes,
Um,
it's not. It's not, well, it's on the other hand, is on the one hand it's not trivial, but on the other hand is also not very complex to see, because it's ITS technology, and ITS is actually easier to understand because it just relies on algebra rather than on more advanced mathematical concepts. So it's not actually not that hard to see. And one of the things we want to show is we want to publish a mini, what we call a mini paper, that actually kind of tells the story of this technology, or the maths of this technology, but in a way that are hopefully accessible to a larger community, larger, not just specialized cryptographers, but also kind of general developers who understand a little bit of maths.
why do you think this kind of approach hasn't been implemented before?
Um, there's been a lot of work on the linear side of protocols, and then on the nonlinear side, people tend to work with FHE or with garbled circuits. So it's like from the three approaches, the first one has been left mostly to solve linear operations. but the other two, and for the nonlinear operations, the other two are used. But the other two have also like additional complications, like FHE is it has very heavy machinery, so it kind of it's low when you evaluate a circuit using FHE. And garbled circuit, the evaluation is fast, but it requires a large representation of the circuit. And so very little has been done, I think, on the LSSS side to maximize those multiplications, so that the efficiency of those multiplications. And and also people have maybe not tried to combine elements from homomorphic encryption with elements from LSSS, from linear secret sharing, to tackle this problem. Maybe they have focused on more on building kind of pure solutions either on the one side or on the other side of these two categories. That's kind of one way to think about it.
Yeah, so it's something to do like the siloed nature of when you get really specialized into some sort of field, do you think? And then that just kind of lends itself to you want to build more on what's already existing rather than just merging things that are kind of separate in a way.
Yeah, that's it. Each field is very complex, and so there's very few experts who are able to innovate in one field and in the other. So each typically they focus on one, and that leaves this combination of things more unexplored, because of the difficulty of merging things and ideas together.
At what point did you start to see this relationship that could be, or this bridge that could be built? When those kind of thoughts started emerging, what was the process of kind of having a feeling that there could be something made here into fleshing it out?
Um, it was an iterative process, so it was a trial and error of many things, many weird pathways that took to nowhere, because the number of possibilities is very large. So it looks pretty much like finding a needle in a haystack, because you're kind of doing a branched search. You take one decision, you make one decision here, it takes you nowhere. Then you take one step back, make the other decision. Is this type of mazed problem solution or finding, where you try to find the exit of a maze. And there's a lot of trial and errors as well. The only thing that is an advantage here is that the trial and error takes place on paper. You don't need to build stuff to realize if it works or not, compared to other disciplines like medicine, where you really need to test the meds against in a living tissue of cells, and then in animals, and so on. So the process goes much faster, but it's a process of you know
Brute force.
trial and error, and yeah, completely.
Yeah, yeah. Yeah, that makes sense. Because I was trying to imagine how do you arrive at a conclusion, and it just sounds like it would be a very arduous process. But I'm glad you figured it out. I'm really excited to see it being developed, and being able to people being able to use it for things. And with that being said, what stage are you in right now into developing it?
So we have an existing network. At this stage, is all the nodes are controlled by us. So we call that kind of a DevNet. And soon we'll be moving to a testnet, where we will invite the FEs we've been working with. And then the ultimate step is to open that to the wider audience. So it's not going to be long, but it's kind of the three steps we're taking in our roadmap. And and essentially that's kind of the technology level. At a more strategic level, we've been busy building this initial network, and now we are kind of changing gears. We are taking a step towards opening what we've built to the community. And yeah, that's what we're going to be publishing a number of mini papers, we call them, each one with prototypes of different aspects of the technology in public repos, so that people can still start playing with that technology. Some of them are about core ideas or kind of more mathematical ideas, like a first paper we're going to be publishing very, very soon, and the other ones will be more about essentially giving examples of how to use those core ideas in specific verticals in specific use cases, and they also will come with Python code. And so that's we're really excited about this because it's kind of a turning point in the company where we're gonna start opening a lot of things to the community, and hope to get a lot of feedback from the community and collaboration starting with community. Yeah, so that's really where we are.
Awesome. Do you have a timeline or an estimated date where people are going to be able to try to build things on Nillion?
So it's gonna be like progressive. Like for example, on the on 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 the week of the 7th of November, we're getting this first paper published with some code already, so people can start playing with that code. If people want to, kind of build beyond that and also kind of test our internal network, they can always approach us as FEs. But then, as I said before, the idea is to actually end up opening that infrastructure to people on a number of stages. So it's hard for me now to say which stage for each one of those stages, but what I can say is that it's going to happen very soon.
Awesome. And you mentioned the FEs quite a few times. So how does it look like? Is it a program? How does it structure like? If someone wants to approach you guys to become one of the founding entrepreneurs, how does that work at the moment?
Yeah, so it's a very simple process. You actually express interest, just send an email to, for example, andrew.yo or a@nillion.com for, to make it easier, and express interest that you want to join the program. And then essentially what you can do is start building with us. So we will tell you what is the infrastructure that is built, what are the things that you can work with. We receive also information from your problem, the problem you want to tackle. If there's things that we don't cover yet, then we factor that into our roadmap so that we can address those in a short term and actually provide you with sufficient features to solve your problem. And that's it. It's at the beginning of a normal collaboration where you can have early access to the technology and the infrastructure that we're building.
Awesome. It's been a pleasure having you here and have you explain and kind of share the new exciting things you guys have coming on. I'm super excited to see things evolve and all this ecosystem coming to life and being integrated with all kinds of different businesses from Web3 and Web2 and everything in between. So
Thank you.
thank you. Thank you.
Yeah. Thank you so much for having me here. It's really a great pleasure speaking to you, and yeah, we're really excited because of the moment this time represents. We're releasing, as I said before, this mini paper. So I think by the time this podcast will be published, will be already out there. So please do check it out. You can find it pinned on our Twitter account, and just join the conversation. We'll be glad to have you there.